Hello everyone, this is Aman from Team TopCoders and this is our demo video for problem statement number 1584 for the SIH 2024. Firstly, let us go over the website we have devised in accordance to the problem statement. The Rail Anomalies Detection System website is used to display the detected wear and tear, defects, fractures, etc. It also marks these defects on the map as we can see on the screen. Initially, the hardware is used for defect detection and thereby the data is processed by the AI model and is thereby stored. This resultant data is stored into the stipulated final data table. We have two records in the final data table, which are the anomalies and the latitude and longitudinal coordinates of the defect data. The website fetches the data from DynamoDB and displays it on an integrated map. We have utilized the geolocator API to display the precise locations of anomalies. In the future, our platform will also include functionalities such as feedback and complaint section powered by NLP integration. After the data is fetched, it will roughly look like this. The data includes the different types of anomalies and coordinates of the defects. As we can see here, we have shown a case of worn or burnt wheels along with other n-named anomalies. This data is illustrated in a list format as well as on the map format. Here, we have the list format and up above we have the map format. The exemplary anomaly is shown, which indicates the burnt wheels case as well as the accurate latitude and longitude of the defect detected. This is also accurately marked on the map. The second case shows the anomaly of wear and tear as well as the latitude and longitude.
Moving on, here we have a 3D CAD model for the construction of both the defect detection systems. Firstly, we have the acoustic microphone and aux microphone system. Starting at the side boggy wheelbase, we have a defect detection mic that picks up audio from the railway tracks. This data is thereby sent onto the Raspberry Pi 5, which is connected to the GPS module as well. These apparatus help us to upload data onto the cloud on given access to Wi-Fi or 4G networks. Up upon the roof, we have our aux mic that will be used for noise cancellation by recording noise from around the train that may arise from unforeseen circumstances. Next up, we have our ultrasonic transmitter and receiver defect detection system that is installed upon the side wheelbase. Below here, we have our transmitter and receiver system that detects the defect from the tracks. This apparatus is then connected to the Raspberry Pi 5 and GPS module for further data propagation. That concludes the construction of our defect detection system. Here we have the circuit diagram of the prototype. This is the ASP. The ASP receives data from the GPS module as well as the mic. The GPS sends data to the ASP using serial bus, and while the mic module uses I2S protocol. Moving forward, this is the physical depiction of the circuit diagram. I will be explaining the components and the functionality of the circuit. As you can see, this is the ESP. It is connected to a GPS and a mic. This mic module we are currently using is an INMP441 mic module. The GPS is Neo 6M GPS module. The ESP collects data from both these sensors and sends it over to the AWS server. It sends data through Wi-Fi, or we can also use 4G network. Currently, it's using Wi-Fi. As you can see, these are the messages which are received by the AWS server from our ESP. These are dummy messages at this moment. It then uploads these messages to the DynamoDB database, which is the AWS database. This data is then further sent into ML model for further processing.
Moving forward, we shall now comprehensively go over the AI model used. Our system captures audio recordings clipped into 5-second intervals and stores them locally. When the train halts at a station, the stored files are uploaded to the database in base64 format to optimize space. The model retrieves these files, extracts MEL frequency, which apply fast Fourier transform to derive 14 key audio features, and simultaneously processes audio from the auxiliary mic to perform noise cancellation. This noise reduction is critical for enhancing anomaly detection, as background interference can significantly reduce the model's efficiency. The clean data is fed into our anomaly detection model, which employs a random forest and logistic regression pipeline. While currently trained to detect 3 specific anomalies, the system has potential for expansion with more diverse datasets. If the model identifies an anomaly, it tags the specific issue, stores it alongside GPS coordinates, and uploads this information back into the database. This process database This process data is thereby displayed on our website's GeoMap interface. Lastly, we shall be going over a flowchart that describes the entire process from defect detection all the way until data procurement. Firstly, on the left-hand side, we have a first set of defect detection apparatuses, which consists of the defect detecting microphone as well as the auxiliary microphone for noise cancellation. On the right-hand side, we have a second set of defect detection apparatuses, which consists of the ultrasonic transmitter as well as the receiver. The GPS module as well as the Raspberry Pi 5 are common to both the constructions as they help in data storage and geographical marking of the errors, which is required by both the systems. In this way, we have a dual cross-verifying defect detection system in place. Now, after the Raspberry Pi 5 module reaches a station or a point of connectivity, it uploads its data onto the cloud, where the integrated AI model transforms the file type to scan for defects. After the data is processed, the system marks the defects onto the map. This data, after many layers of encryption, is accessible on the website as well as the mobile application by a select group of individuals only. That marks the end of our flowchart as well as our demo video for the problem statement. Thanks for listening.